So let's talk about how you change something's momentum. So remember that momentum is equal to the mass of an object times its velocity. So we're going to apply a force over time, and that's going to change the momenta, which is the plural of momentum, of the interacting objects. So to change an object's momentum, you're going to apply a force over some time, and that's going to change the momenta of the interacting objects. So a large force applied over a short time can change the momentum the same amount as a small force over a long time. So you can imagine if you are trying to slow down a car, you can slam on the brakes. So we have a car here. So the car is going very fast. You can slam on the brakes and slow it down in a short time, or you can gently apply the brakes and slow it down over a longer period of time. In the end, you're still slowing it down the same amount. You're just doing it over a different amount of time. The change of momentum is called an impulse. So the total momentum change, is equal to the net, or the total force applied over time, and that we call impulse. All right, so let's talk about how Newton's second law and momentum are related. All right, so here's Newton's second law in terms. So Newton's second law in terms of momentum. So here we have delta P over delta T. So that's change of momentum over change in time. All right, so we can rewrite delta P as equaling delta mv. So that's the change in momentum, because momentum is just mass times velocity. So we can rewrite that as m delta v. So now we're looking at our net force is equal to m delta v over delta t. And this term, delta v over delta t, is equal to acceleration. So now we have F net is equal to ma, which is how we think of Newton's second law in general. All right, so here we have the equation J, which is impulse, equals F delta T. So force times delta T, which if we look up here, we have F net equals delta P over delta T. So if we just rearrange the terms here, we end up with F net delta T equals delta P, which is what we have here. F times delta T equals m delta V, which is what we have right here. So this is the impulse momentum theorem. So this tells us that the impulse is force times the time, which is the same thing as the change of momentum. All right, so let's look at a couple of examples here. So we want to know, what is the impulse delivered to a 60-kilogram driver when his car, moving at 20 meters per second, hits a wall and stops? All right, so we're looking for impulse. We know that the mass of the driver is 60 kilograms. So he's originally moving at a velocity, so his initial velocity, v naught, is equal to 20 meters per second, Its final velocity is equal to 0 meters per second. So looking at our equation here, the impulse momentum theorem, we have J is equal to F delta T equals M delta V. So we have a change in velocity, so we're going to use, and mass, so we're going to use this part of the equation, M delta V. So we have impulse is equal to mass times, now our final velocity is 0 meters per second, minus our initial velocity, which is 20 meters per second. So we have 60 kilograms times minus 20 meters per second. That gives us an impulse of minus 1,200 kilograms meters per second. So the driver's momentum changed by minus 1,200 kilograms meters per second. Okay, so for problem number 2, if this collision took place in 0.01 seconds, what force does the driver experience? So we already have our impulse from the previous problem. So now we want to figure out the force. So here we're going to use impulse is equal to force times delta T. So we're going to solve for force. So divide both sides by delta T. We end up with force is equal to impulse divided by the amount of time. So we have our impulse is 1,200 kilograms meters per second. Divide that by 0.01 seconds, and we end up with a force of 120,000 newtons. Remember, a newton is equal to kilograms meters per second squared. So we have kilograms meters per second, and then we divide it by seconds, so that gives us our seconds squared. So we have a force of 120,000 newtons acting on the driver. So a lot of force. Okay, so for example 3, we want to know if the airbag deploys and increases the time to 0.25 seconds, what force does the driver feel? Okay, so similar problem here. So we have our impulse is equal to force times delta T. So now we're still trying to find the force here. So we're going to solve for force. So force is equal to impulse divided by delta T. So we have our impulse, again, is 1,200 kilogram meters per second. Divide that by our time, 0.25 seconds. Let's see what the difference is. So that brings our force to 4,800 newtons. So if we were to compare 4,800 and 120,000, it's about 1/25 of the force. So by deploying an airbag, the driver feels 1/25 of the amount of force in that collision, which is exactly why we use airbags.